Welcome to this third lecture. Now, the same two port reciprocal network, we enforce symmetry in the network. Generally, filters, most of the times we design symmetrical filters. The two port network is symmetrical. What do we mean by symmetrical? When I said this two port, that time I said this is Z1, Z2, Z3. So, in a T section, as I already said, any two port network, whatever may be the interconnection, can be always represented like this. Now, this Z1, Z2 different, that is a asymmetric network. If I enforce symmetry, then Z1 is equal to Z2. So, what happens to Zi1, my image impedance Zi1, and you see the expressions of Zi1 and Zi2 already derived. The moment Z1 and Z2 are same, they become equal. So, for a symmetric network, Z1 and Zi2 are equal. That we generally call Z0. What is Z0? A very, very important concept called characteristic impedance. So, for a symmetrical network, I have only one characteristic impedance. For a non-symmetrical reciprocal network, I have two image impedances, but here it is one. So, what is the concept of characteristic impedance? That if I terminate with characteristic impedance, then the source with characteristic impedance Z0 will see that input impedance is also Z0. So, it can deliver maximum power. Okay. But now, so we see that we have characteristic impedance. Let us see what is its value in terms of ABCD parameters. We already seen that when we enforce Z1 is equal to Z2, that means the symmetry Z1 becomes Zi2. So, that implies that we have already earlier derived Zi1 is equal to AB by CD, and this is BD by AC. So, that becomes A is equal to D. You all know in two port parameters, transmission parameters, if symmetrical network A is equal to D, it comes from here. So, what happens to the value of Z0? It is simply B by C. And so, now you see that for a symmetrical reciprocal network, I can characterize the network by only two parameters. One is this Z0, another already we have seen, it is gamma. So, Z0 and gamma are sufficient to characterize a network. So, by Z0 we will understand what will be our impedance level, if there is an impedance mismatch, etc., and with gamma we will enforce whether the frequency is passed or not, whether it is attenuated or not. So, let us now express the ABCD parameters we are so familiar with in terms of Z0 gamma. That means, from now on we will specify only Z0 and gamma for filter, etc., specifications. So, we should have a mapping between ABCD, etc. So, you can easily do that express ABCD in terms of Z0 and gamma, because now our description will be in terms of that. So, you can start from that AD minus BC is equal to 1 and also A is equal to D. So, with this you can now find out that, let us decide that what will happen to then if we put this A is equal to D, we get BC is equal to root over A square minus 1, and also we know that B by C is Z0 square. You see this one Z0 we have found as B by C. So, this from this you can find out the value of C is root over A square minus 1. by z naught and b is z naught root over a square minus 1, but and what is e to the power gamma? E to the power gamma, earlier we have seen it is AD plus BC. Now, in terms of this, I can write it as A plus root over a square minus 1. So, this equation I can solve. So, A will be expressed in terms of e to the power gamma or gamma. So, by doing that, I can see that e to the A becomes e to the power 2 gamma plus 1 by 2 e to the power gamma, that is nothing but e to the power gamma plus e to the power minus gamma by 2, which is nothing but cos hyperbolic gamma. So, A is nothing but cos hyperbolic gamma. Now, put this, B is already expressed in terms of z naught and this z naught value you know, let me write z naught is root over b by c. So, you can solve for and see that b will be equal to z naught sin gamma. Please all of you do these exercises. I am just writing, you cannot memorize all these things, but I am telling you the way. So, please do these manipulations. It requires a bit familiarity with hyperbolic functions, and c is equal to 1 by z naught sin hyperbolic gamma and d is equal to cos hyperbolic gamma. So, you see that this expression, that means now I can clearly write that A is equal to cos hyperbolic gamma, B is equal to z naught sin hyperbolic gamma, C is equal to 1 by z naught sin hyperbolic gamma and D is equal to cos hyperbolic gamma. So, you see that actually here from also you can see that ABC D parameter was not needed because A is equal to D for a symmetrical network, and this is the description that any ABCD parameter I can express in terms of two quantities gamma and z naught. So, that is the beauty. Now, we know that we are in the right path. What we will do now? We will put the filter condition. So, for a filter, as I said, what is a filter? That it will allow some bands to pass, it will stop all other bands. So, we demand that now network, two-port network is in terms of gamma and z naught. What is our demand? That if it is to be a filter, so gamma in pass band should be lossless. We want that gamma, the propagation constant, should be lossless, then only the circuit won't attenuate power, also not store power, it will be able to deliver it to the port 2. So, but you know that gamma is a complex quantity. As I said, how we define that input volt ampere, output volt ampere, their ratio that we call e to the power 2 gamma. So, gamma is that. Now, you are also familiar that generally this complex quantity we write as two part alpha plus j beta. Alpha is the attenuation constant, beta is the phase constant. For any wave, for any electromagnetic wave, this is true. So, when we say that alpha in pass band should be lossless, what we basically say that alpha should be 0 over the whole pass band, that there should not be any attenuation. And what happens in stop band? Stop band, we want that it should be lossy. So, at least alpha should not be equal to 0. Okay. And we have already decided that to have this passband alpha is equal to 0, we will use only reactive elements. Now, there is a theorem which we will now see. The theorem says that for a symmetric two-port reciprocal network of pure reactances, if the characteristic impedance is a pure resistance, the attenuation constant is 0. If the characteristic impedance is a pure reactance, their attenuation constant is non-zero. So, for this symmetric two-port reciprocal, this is a theorem of Everett. Symmetric two-port reciprocal network made of pure reactances. The theorem says that if Z0 is pure resistance, Z0 is pure resistance, then alpha is equal to 0, and if Z0 is pure reactance, alpha is non-zero. Let us prove this theorem. So, we will now prove this theorem. Since the network is made of pure reactances, can I say that network, these are all, instead of Z, they are J x1, it is a symmetric network J x1 and J, let us say x3, instead of Z1, Z2, Z3. Now, this may be plus minus whatever. So, if this is the case, then can I say that ZOC and ZSC, which we already saw, they are also pure reactances. Okay. We have seen that Z0 is equal to root over ZOC into ZSC. So, open circuit and short circuit cases. So, they will be, because we have seen there are various combinations of these, they will be also pure reactances. So, let us consider that ZOC, let us call it either plus or minus the pure reactance. This is, let us call plus or minus JXB. That means XA and XB pure real positive numbers. You agree that this should be, because since I have incorporated J, XA and XB are positive real numbers. Now, let us see, there can be several cases. Case 1, 2, I am proving the theorem. The theorem is important for filter design. Now, let me say what is ZOC, what is ZSC. Then we know Z0 square is equal to ZOC, ZSC, and we know tan this square is ZSC by ZOC. So, we will make table. So, case 1 is, let us say that this ZOC and ZSC, they are of same sign. So, it is plus JXA, it is plus JXB. Oh, no, not of same sign, sorry, minus JXB. Then what will be Z naught square? It will be simply XAXB. And what will be this? ZSC by ZOC, it will be minus XB by XA. Case 2, this is minus JXA, this is plus JXB, this will be XAXB, this will be minus XB by XA, this is plus JXA plus JXB, this is minus XAXB, this is XB by XA, this is minus JXA minus JXB minus XAXB, XB by XA. So, you see that time I said I have these possibilities. So, I have taken all permutations of these. From here you can see that case 1 and 2, Z naught is real. That means Z naught, it is a characteristic impedance. It is real means this is a pure resistance, and tan hyperbolic is imaginary, because tan this square is minus. So, tan hyperbolic will be an imaginary number, and in case 3 and 4 I have marked that by red. You see Z naught is imaginary and tan hyperbolic is real. So, let me write this thing, that in case 1 and 2 Z naught is real and tan hyperbolic is imaginary. In or for cases 3 and 4, Z naught is imaginary and tan hyperbolic gamma is real. Still I have not proved the theorem, because theorem said that if Z1 is real, alpha will be 0. If Z1 is imaginary, there will be non-zero alpha. I have not reached there. So, I need to do that to prove the theorem. So, part 1 is this. Then let me then write what is tan hyperbolic gamma. Tan hyperbolic gamma is nothing but tan hyperbolic alpha plus j beta, and that is equal to sin hyperbolic alpha cos beta plus j cos hyperbolic alpha sin beta by cos hyperbolic alpha cos beta plus j sin hyperbolic alpha sin beta. Now, numerator denominator both are complex number a plus jb. So, I rationalize the denominator. So, that becomes, after some manipulation, simple manipulation, cos hyperbolic alpha sin hyperbolic alpha plus j sin beta cos beta by cos hyperbolic alpha square cos square beta plus sin hyperbolic square alpha sine square beta. So, denominator is pure real. Now, I can talk of that when tan hyperbolic gamma is, we have seen that in this case tan hyperbolic is imaginary. So, tan hyperbolic is pure imaginary, cos hyperbolic alpha, sin hyperbolic alpha. So, tan hyperbolic alpha to be imaginary, I require that this part should go to 0. Now, here you see cos hyperbolic alpha always is greater than 0, because it is e to the power alpha plus e to the power minus alpha by e to the power by 2. So, it cannot be 0, cos hyperbolic alpha cannot be 0. So, the only possibility is this implies sin hyperbolic alpha is equal to 0. What is sin hyperbolic alpha? That means e to the power alpha is equal to e to the power minus alpha. That means that alpha is equal to 0. So, theorem, where is the theorem? Theorem said that when Z naught is pure resistance, alpha is equal to 0. You see, Z naught is pure resistance. From this I got that alpha is equal to 0. So, okay. And let us see the other option. When tan hyperbolic gamma is pure real, what I get, you see, this thing is pure real, that means this part should go to 0. I demand sin beta, cos beta should be 0, and also cos hyperbolic alpha, sin hyperbolic alpha non-zero, because this also may go to 0, then whole thing will be 0, but I require that this is non-zero, but cos, as I said, cos is always greater than 1. So, no problem, it demands as cos this is always greater than equal to 1. So, what we demand is sin hyperbolic alpha is non-zero. So, that means alpha is non-zero. Alpha non-zero means the attenuation constant is non-zero, that means there is attenuation. So, that proves the theorem that when, so what it shows, let me go to my cases, that it says in this case when Z naught is real, there will be no attenuation, and when Z naught is this, there will be definitely attenuation. So, can I not say that if I enforce this condition, this is my pass band condition and this is my stop band condition of a filter. So, I will do that. So, but you also observe here that, so this is my filter pass band, I will go from here, but here I have one demand that ZOC and ZSC, they should be of opposite sign. Now, ZOC, ZSC, they are, that means that, or I will see that. So, let me now see my T section. I can also see it with pi section, but the, so it is a symmetrical, and instead of earlier I was calling it Z1, now people call it Z1 by 2, because there are two in series. So, okay. Now, remember, obviously Z1 and Z2 they are pure reactances. We want to derive the propagation constant of this gamma of this network. Already we have done tan gamma. So, from there we will try to see enforce the passband condition. So, port 2, let us make that this is open circuit condition. So, that time we know we call it ZOC, and what will be that ZOC? ZOC is easily Z1 by 2 plus Z2, that is equal to Z1 plus 2Z2 by 2. Now, I put that port 2 is shorted. This is Z1 by 2, Z1 by 2, Z2, and this is ZSC. So, what is ZSC? It is, you can easily see Z1 by 2 plus parallel of Z2 and Z1 by 2. So, that if you do, it will become Z1 by 2 plus Z2 parallel Z1 by 2, and that is equal to Z1 square plus 4 Z1 Z2 by 2 Z1 plus 2 Z2. So, I got ZOC, I got ZSC. So, I can easily now find what is the characteristic impedance Z0. Z0 I know always this is true. I have expressions for them. So, if you put, it becomes Z1 square plus 4 Z1 Z2 by 2. Already we have seen in that table that this gamma becomes pure imaginary. So, this is the stop band. There ZOC and ZSC, they should be opposite sign. So, because that only makes, you see, the ZOC and ZSC, their opposite sign makes the characteristic impedance real. Otherwise, if they are of same type, then this is imaginary. And what happens to the other? So, characteristic impedance we have find. What is the other parameter of the two port symmetrical reciprocal network? Gamma. So, what is tan gamma? We know that is ZSC by ZOC, and if you do this, that will become root over Z1 square plus 4 Z1 Z2 by Z1 plus 2 Z2 square. Now, this we want this tan gamma should be imaginary in the passband. So, our demand is that in the passband Z1 square plus 4 Z1 Z2 by Z1 plus 2 Z2 square should be less than 0. Consider this case 1 in the table. We will now confine ourselves to this case 1 and 2. In case 1, ZOC is plus JXA, this is minus JXB. So, let us put it case 1, ZOC is plus JXA, ZSC is minus JXB. So, what happens to Z1 plus 2Z2 2 by 2, this one Z1 plus 2Z2 by 2 becomes JXA, and Z1 plus, so this 2Z2 whole square, that becomes minus 4x square. We know xa is a positive real number, so Z1 plus 2Z square, that is less than 0. So tan beta, that means in passband we know this tan beta value is this. Now this is less than 0, so this whole thing less than 0, this is less than 0, this needs to be positive to satisfy this. So we can say that tan gamma imaginary to be imaginary, Z1 square plus 4 Z1 Z2, that needs to be greater than 0. So this is from case 1. That means first case of the passband we know this. Let us see the case 2. There we have seen ZOC is minus JXA. This is case 2. ZOC is minus JXA, ZSC is plus JXB. So with this, what happens to Z1 plus 2Z2 by 2? That becomes minus JXA. So what happens to the square of this? 2Z2 square, that is again minus 4x square, that is again less than 0. So same condition, that here also tan gamma to be imaginary, we require Z1 square plus 4 Z1 Z2 greater than 0. So the condition in the passband, if we want to have passband without any attenuation, then condition is Z1 square plus 4 Z1 Z2 greater than 0. Now Z1 and Z2, they are reactive elements. So again there will be various sub cases. So I can say sub case 1 or sub case A, because there will be various choices of Z1, Z2. We should remember that Z1 is equal to Jx1, let us choose this, and Z2 is equal to Jx2. Then we can write what happens to Z1 square plus 4 Z1 Z2, that is minus x square minus 4 x1 x2 greater than 0, or x1 square plus 4 x1 x2 is less than 0. So since x and x1 and x2 are positive real numbers, this is not possible. So I say that this subcase A is not possible. Similarly, subcase B, there will be Z1 is equal to minus Jx1, Z2 is equal to minus Jx2. Again we will get the same condition, x1 square plus 4 x1 x2 is less than 0. So again not possible. Subcase 3, subcase C, here let me take this as Jx1, Z2 as opposite sign minus Jx2. If you do this, so what is this value Z1 square? Always we are evaluating this now, Z1 square plus 4 Z1 Z2, that should be greater than 0. This is the condition to achieve passband. So we are doing this, and getting this 4x1 x2 is greater than x1 square. Now, as x1 is greater than 0, so 4x2 will be greater than x1, or x1 by 4x2 is less than 1. Also, x1 is greater than 0. So, combining this, the condition is that 0 less than x1 by 4x2 less than 1, or I can say, or 0 less than jx1 by 4 jx2 is less than 1, or 0 greater than jx1 by 4 minus jx2 is greater than minus 1, or 0 greater than z1 by 4 z2 is greater than minus 1. So, this is possible, that means here if we do this and enforce this condition, it boils down to that z1 by 4 z2, this ratio should be between 0 and minus 1, and let us see the subcase D, that will be z1 is equal to minus jx1, z2 is equal to plus jx2. Again, if you do, you get the condition that 0 is z1 by 4 z2, then minus 1. So, this shows that you can have the passband of filter should be in the range, this z1 by 4 z2, this number should be within this range. And where is the stop band of the filter? Stop band of the filter there are two possibilities for that. We have already seen that z1 by 4 z2 that is greater than 0, or z1 by 4 z2 that is less than 1. This is mathematics. We will see in the next lecture what is the implication of that. But what we have done here, we have found out that if you want to have passband, the two reactances, their impedances z1 and z2, this z1 by 4 z2 should be within this range, then only you can have passband. And if you choose z1 by 4 z2 either this or this, you get stop band of filter. Thank you.